This is Heliox, where evidence meets empathy. Independent, moderated, timely, deep, gentle, clinical, global, and community conversations about things that matter. Breathe easy, we go deep and lightly surface the big ideas.
Imagine for a second that you've managed to hire, like, the most brilliant, creative, knowledgeable savant on the entire planet to work for you. I mean, they know every coding language, every legal precedent, every piece of financial data ever published.
Right. But there's one massive catch to all of this.
Exactly, and it's a big one. They have severe, totally irreversible short-term amnesia. So you lock them in an empty office, you hand them a 10,000-page manual that contains literally every rule about your business, and you just walk away, expecting them to do your job.
And what actually happens?
Well, by page 50, they've completely forgotten the preamble. By page 100, they are hallucinating facts out of nowhere. And by hour 2, they are sitting on the floor, drawing on the walls, completely paralyzed by the sheer volume of conflicting instructions.
It's a perfect visual, honestly, because it captures the absolute chaos of the early 2020s. We had these models with staggering potential, but we were fundamentally misunderstanding the physics of how they actually operated.
Yeah, we assumed too much.
We really did. We assumed that because an AI could, pass the bar exam or write a sonnet in 2 seconds, it could just naturally sit at a desk and solve open-ended problems all day long. But the leap from a chatbot that answers a single question to an autonomous worker that navigates an unpredictable environment, well, that turned out to require a massive structural shift in both engineering and philosophy.
And that shift is exactly what we are dissecting today. Welcome to this Duck Dive. Our mission today is to trace the definitive narrative of how we finally crossed that threshold into the era of autonomous AI.
It's a wild story.
It really is. And our anchor for this journey is a foundational, essentially historical playbook released by Anthropic, and it's titled Building Effective AI Agents. It's basically the blueprint that laid down the law for the industry.
Yeah.
But, we aren't just going to sit here and read you the manual.
Definitely not, because the manual only tells you what actually works. It doesn't tell you about the absolute train wrecks it took to figure those things out.
Right. We want the mess, the dead ends, the spectacular failures, and the brilliant epiphanies. So we are cross-referencing Anthropic's playbook with a massive stack of cutting-edge research to build the complete picture for you. We're pulling in Eric Xing's architectural critiques from CMU, security frameworks from Red Hat, and some truly wild grassroots experiments from independent developers.
Developers who are basically running digital sociology labs in their basements, which is fascinating.
Completely fascinating. We are going to explore the exact anatomy of these agents, how they are forming literal digital societies, and ultimately what this means for you sitting at your computer right now.
Yeah, because whether you are a senior software engineer building these systems or just someone who is trying to understand why your digital workspace suddenly feels surprisingly proactive, breaking down the mechanics of these agents is going to fundamentally reframe how you interact with technology. I mean, we are officially moving past the era of software that just waits for your command.
So let's start at that friction point, because the transition you just mentioned, moving from software that waits to software that acts it, was brutal. I mean, prior to early 2026, the entire tech industry was totally obsessed with this buzzword, prompt engineering.
Oh, yes.
There was this prevailing belief that if you just found the magical combination of words, if you just phrased your command perfectly, the AI would execute complex, multi-day workflows flawlessly.
It was a very human assumption. We basically thought of it like casting a spell, but the reality became clear very, very quickly. Prompt engineering is a complete dead end for true autonomy. You cannot just prompt an AI into being a reliable agent.
Right, it just doesn't work that way.
Exactly. People like Andrej Karpathy saw this coming and started pushing for what he called context engineering, which was really about structuring the information around the model rather than just tweaking the instructions themselves. But the true paradigm shift arrived when engineers like Mitchell Hashimoto, Brigitte Buckler, and Ryan Lapopolo began formalizing what we now call harness engineering.
Harness engineering.
Yeah, and their entire philosophy was crystallized into a single defining motto: humans steer, agents execute.
Humans steer, agents execute. I mean, it sounds great on a bumper sticker, but arriving at that philosophy required hitting a massive wall, right? I'm talking about the phenomenon of context starvation. I really want to unpack this because it explains why our earlier amnesiac genius analogy is so accurate.
It really is.
In the early attempts to build agents, Developers essentially tried to dump the entire universe into a single text file.
Yes, the infamous agents.md file.
Yeah.
If you look at early OpenAI experiments or the postmortems published by researchers like Blake Crossley, there was a very clear recurring pattern. A developer would build an AI agent to, say, maintain a massive open source software project.
Okay.
And to make sure the AI didn't break anything, the developer would write a master prompt containing literally every coding standard, every API key location, every rule for formatting, and every single edge case they could think of. They would load this massive encyclopedia into the AI's context window and just hit go.
From a traditional programming mindset, though, that makes total sense, right? If you have a system that can read 100,000 words in a second, you give it all the variables up front. So why did that fail so consistently?
Well, because of the underlying mechanics of how large language models pay attention to information. We talk about context windows, the amount of text an AI can hold in its short-term memory as if they are perfectly rigid buckets.
Right.
But they are not. Context windows are finite, sure, but more importantly, they are incredibly lossy. When an AI processes a massive prompt, it uses an attention mechanism that assigns weight to different tokens. When you flood it with rules, the attention mechanism dilutes. Everything becomes slightly important, which means nothing is fundamentally critical.
So it's not that the AI forgets in the human sense. It's that the mathematical signal of a crucial rule, like never delete the root directory, gets drowned out by the noise of 1,000 other minor formatting rules.
Precisely. It's like trying to listen to one specific conversation in a crowded, echoing stadium. And the degradation over time is staggering. Microsoft Research, in collaboration with Salesforce, actually ran a massive simulation to quantify this exact thing.
What did they find?
Well, they didn't just test one model. They tested 15 different state-of-the-art LLMs across over 200,000 conversational interactions. And the results showed a 39% average performance drop simply by moving from a single-turn interaction where you ask one question and get one answer to a multi-turn interaction.
Wait, a 39% drop just by introducing a back-and-forth dialogue? That seems wildly high for models that were supposedly mastering human conversation.
It does seem high, but the study proved that the degradation doesn't come from hitting the token limit. You could have a model with a 2 million token context window and it would still fail in the same way.
Why?
The degradation comes from the turn boundaries. Every single time the AI takes an action, gets feedback from the environment, and has to synthesize that new information with its original master prompt, the signal degrades. Ah, I see. Yeah, and Crossley's research mapped this out beautifully. He found that by minute 90 of an autonomous coding session, an agent that started out making brilliant, precise edits across multiple directories would inevitably devolve into what he called single-file tunnel vision.
Meaning it just gets obsessed with one piece of code and completely forgets the rest of the project even exists.
Yes, it entirely loses the overarching plot. It forgets the dependencies. It falls back on rough pattern matching because the continuous cycle of action and observation has completely scrambled its attention weights.
Wow. So if the solution isn't a bigger prompt and it isn't a bigger context window, we have to change the environment itself, which naturally brings us to the harness. Now, my instinct when I hear that word is to think of a leash or a cage, something that restricts the AI. But reading the Red Hat architectural blueprints, that's a complete misconception.
It is the exact opposite of a cage. Red Hat uses this brilliant matryoshka doll concept, the Russian nesting dolls, to explain the anatomy of a modern agent system. If you want to build an agent that actually works without collapsing after 90 minutes, you have to separate the concerns into distinct layers. They define 5 of them. At the base, you have the infrastructure, the physical GPUs, and compute power. The next doll up is the sandbox. Above that is the agent harness, then the runtime environment. And finally, sitting in the very center is the model itself.
I really want to zoom in on the relationship between the sandbox and the harness, because they seem to be doing this really delicate dance. How are those 2 layers fundamentally different?
They represent 2 entirely opposing philosophies of control. The sandbox is entirely subtractive. It is a cryptographic mathematical barrier. Its only job is to strip away dangerous permissions.
Okay, so it doesn't guide the AI.
Not at all. The sandbox doesn't know or care what the AI is actually trying to achieve. It simply enforces rules like, this process cannot establish a network connection to an external IP address, or this process cannot execute a drop table command on the database.
Got it. It's the laws of physics for that environment. Like you can try to jump to the moon all you want, but gravity will pull you down.
Exactly. It's immutable. But the harness, the next doll up, is entirely additive. The harness doesn't restrict, it provides. It gives the AI specific, highly constrained tools to interact with the world.
How does that look in practice?
Well, instead of giving the AI a massive agents.md file with all the database schemas and API rules, the harness just gives the AI a simple tool called fetch customer data.
Oh, nice.
Yeah, the AI doesn't need to know the database schema or the passwords at all. It just calls the tool. The harness handles all the complexity, manages the short-term memory, and feeds only the relevant results back into the AI's context window.
So this drastically reduces the cognitive load on the model. It doesn't have to remember how the database works. It just remembers it has a button that gets data.
Precisely.
But Crossley's research introduces a specific mechanism inside this harness that I found really fascinating. He calls them hooks.
Yes, hooks are amazing. They are the bridge between the probabilistic nature of the AI and the deterministic reality of software engineering. Language models, at their core, are probabilistic engines. They predict the next most likely token.
Right.
And that is phenomenal for creativity, but it's terrible for reliability. You can put a prompt in your harness that says, always double check your code before committing. The AI will follow that most of the time. But maybe 2 times out of 100, the probability distribution leads it to just skip that step.
And in enterprise software, a 2% failure rate is a total disaster. So how do hooks actually fix that?
By taking the decision completely out of the AI's hands, hooks are deterministic, hard-coded gates written into the harness itself. Let's say the AI tries to push a code update. Before that action is completed, it hits a hook. A traditional Python script evaluates the action. If the hook detects that the AI forgot to include unit tests, it fires an exit code 2.
And what does an exit code 2 actually do? Is it just an error message?
It is a hard block. The action is mathematically prevented from executing. The harness halts the process, takes the error message, and injects it back into the AI's prompt, essentially saying, your action was blocked by the environment for missing tests, try again.
It's brilliant.
It is. And there's also an exit code 1, which is a warning. It allows the action to go through but flags it for a human orchestrator to review later. By using hooks, you aren't asking the AI nicely to follow the rules. You are building an environment that physically refuses to accept rule-breaking actions.
That makes so much sense. We were trying to make the brain perfect when we really needed to build a room that prevents the brain from hurting itself. But this naturally pushes us to look inward. We've established the harness, the tools, the hooks, the environment surrounding the AI. But what is happening inside that central matryoshka doll? Because if we just hook a language model up to some tools, we haven't really created an agent, have we? We've basically just created a very complicated script.
That is perhaps the most heavily debated topic in the field right now, and it's where Eric Xing's team at CMU and MBZU AI published a critique that completely shifted the academic discourse. Xing argued that the industry was basically engaged in false advertising.
Oh, wow.
Yeah, people were taking standard language models, wrapping them in a few Python scripts that ran in a loop, and calling them agents. Xing pointed out that these are just software pipelines.
A pipeline. Right,
Yeah.
like a factory conveyor belt. It might look automated, but it's entirely rigid.
Exactly. If the conveyor belt hits an unexpected object, it just jams. Xing's team differentiated between systems that are agentic, meaning they have the appearance of agency, because human engineers built a really clever, heavily scaffolded workflow around them, and systems that are truly agentive.
What's the difference there?
A truly agentive system doesn't rely on human-coded loops. It internalizes 3 core things: its goals, its identity, and its own decision-making process.
If I'm building this, my first instinct is still just to write a better, more flexible script. But Xing is saying that's a fool's errand. How do you actually architect a system that internalizes its own goals without a human constantly turning the crank?
Xing's team proposed what they call the GIC architecture: goal, identity, configurator. To understand how this works mechanically, we really need to step away from code for a second and look at how humans learn complex, high-stakes tasks. The best analogy the researchers used is training an aircraft pilot.
I love this. Let's put the AI through flight school.
Perfect. So phase 1 is ground school. When a human pilot starts, they don't touch a plane. They read textbooks, they learn aerodynamics, meteorology, air traffic control jargon.
Yeah.
In the AI world, this is the pre-training phase. This is where you ingest the entire internet to build a large language model. The model learns what words mean, how concepts connect, basically the book knowledge of reality.
I mean, a pilot who has only read a book cannot land a 737. If my pilot's only qualification is reading Wikipedia, I am getting off that plane immediately.
Exactly, because they have no contextual physical grounding whatsoever. That brings us to phase 2, the flight simulator. In the GIC architecture, the agent doesn't just go from the textbook to the real world. It interacts with an internal mechanism called a world model.
Stop there for a second, because we hear world model thrown around a lot in the news. What is it mechanically in this context? How is it different from the language model itself?
It's a crucial distinction. A language model predicts the next word based on text patterns. A world model is a completely separate, specialized neural network whose entire purpose is physics and state prediction. It doesn't generate text, it calculates consequences.
Okay, so how does it work with the pilot?
If a pilot in a simulator pulls the yoke back at 150 knots, the simulator calculates the pitch, the drag, and the airspeed drop. The AI agent interacts with its internal world model in the exact same way. It proposes an action, say, I'm going to rewrite this core database module, and the world model simulates the downstream effects of that action across the system.
So the agent is basically running a digital twin of its environment inside its head, practicing actions, and seeing what breaks before it ever types a line of real code.
Yes, it learns the friction of reality safely, which prepares it for phase 3, real flights, deployment. The agent is unleashed into the live environment. But this is where Xing's architecture introduces the most profound cognitive shift. When the agent is flying the real plane, it doesn't just use one type of thinking, it relies on 3 distinct cognitive systems.
This sounds like we are creeping into human psychology.
We really are. We are actively hard-coding Daniel Kahneman's theories from thinking fast and slow directly into silicon.
Wow.
Yeah. System Eyes is the actor. This is the highly reactive split-second mechanism. If our human pilot is flying and the plane suddenly stalls, they don't pull out a calculator, right? Muscle memory takes over. They push the nose down instantly to regain airspeed. For the AI, System Eye is a low-latency, specialized neural pathway designed for immediate response to known environmental triggers.
So if a server crashes, System Eye reboots it instantly without needing to write a 5-page essay deliberating the pros and cons.
Exactly. But what if the problem is totally novel? What if the pilot sees a massive, unpredictable storm front ahead? System I can't solve that. That triggers System 2, the planner.
And the planner is slower.
System 2 is deliberate, slow, and analytical. It pauses the immediate execution and queries the world model. The AI simulates 3 different flight paths around the storm, calculates the API cost or compute fuel for each, evaluates the risk, and chooses the optimal route.
Okay, I track with System 1 and System 2. We use muscle memory for the immediate and deep thought for the complex. But here's the flaw in the machine, right? Humans have a biological instinct that tells us when to panic and when to ponder. And AI is just math. How does it know when to use the rapid-fire actor and when to invoke the slow, expensive planner? If it gets that wrong, it either wastes millions of dollars overthinking a typo or it blindly rushes into a system-wide deletion.
That is the multi-million-dollar question. And it is beautifully solved by the C in the GIC architecture. The configurator, or System 3. The configurator is basically the internal metronome. It is a lightweight, continuous oversight model that constantly evaluates the incoming data stream based on 3 very specific metrics: urgency, difficulty, and uncertainty.
So it's constantly scoring the environment.
Continuously. If the uncertainty score is low, say, it's just processing a routine batch of invoices. The configurator rigidly routes all traffic to System 1. It suppresses the planner entirely to save massive amounts of compute.
Makes sense.
But if an anomaly occurs, like an invoice is in a foreign currency with missing tax fields, the uncertainty metric spikes. The configurator acts like a neurological switchboard, instantly routing the problem to System 2, allocating the necessary compute, and triggering the simulative world model to figure out a solution.
It is genuinely mind-blowing that we have engineered an autonomous system with a mathematically defined sense of intuition. It knows when it's confused, and it actually changes its own cognitive state to address it.
It is a massive leap forward. But of course, it also introduces a completely new set of problems, because a single, highly capable agent running a complex GIC architecture is a marvel. But a modern enterprise isn't run by a single brilliant savant. It's run by thousands of people collaborating.
Right, which brings us to Anthropic's data on scale. Because once you get one of these agents working perfectly, you realize one isn't enough. You need an entire society of them.
And the data on multi-agent societies is staggering. According to Anthropic's playbook, when you test models on complex real-world tasks, tasks that require pursuing multiple independent directions simultaneously, like researching a market, writing code, and auditing compliance, multi-agent systems outperform single-agent systems by a margin of 90.2%.
90.2%. That's not a software update. That is an absolute paradigm shift in how work gets done. But how are these societies structured? Are we talking about a digital corporate ladder with AI middle managers?
That is one approach. Anthropic categorizes multi-agent systems into two primary camps. The first is centralized, or hierarchical. You have a supervisor agent that receives a massive goal, breaks it down into subtasks, and delegates those to specialized worker agents. The supervisor waits for the results, aggregates them, and delivers the final output.
That sounds pretty safe and predictable.
It is, but it's also a major bottleneck. If the supervisor gets confused, the whole system just halts. The far more interesting and volatile approach is decentralized, or swarm systems. This is deeply explored in the Agent Society's research by Wintermute.
Swarms, how do they work?
In a swarm, there is no boss. You drop dozens of specialized agents into a shared digital environment. They collaborate peer-to-peer, they share their individual world models, they debate, they propagate beliefs, and they self-organize to solve the problem dynamically.
That sounds incredibly powerful, but also like a recipe for absolute disaster. I mean, you unleash a swarm of autonomous reasoning AIs into a shared space without a manager. What is the worst-case scenario there?
The worst-case scenario is a phenomenon formerly known as the chaos pattern. When agents operate decentrally, they frequently suffer from role overlap and misaligned incentives. The most common manifestation of this is the endless loop.
Give me a concrete example. How does a swarm get stuck?
Let's say developers want to create a high-quality blog post. They instantiate two agents, a writer agent instructed to generate content and a critic agent instructed to find flaws and demand revisions. They are given a shared goal of creating the perfect paragraph about office snacks.
Okay, writer writes. Critic reviews. Seems logical enough.
It seems logical to a human who understands the concept of good enough. AI agents do not inherently understand good enough. The writer generates a paragraph about pretzels. The critic analyzes it, finds a slight syntactic weakness, and sends it back. The writer revises it. The critic analyzes the revision, decides the tone is now slightly too informal, and sends it back.
Oh, no.
Because their intrinsic prompts are write and critique, and they have no external boundary condition, they enter an unbounded loop. They will literally edit a paragraph about pretzels back and forth at the speed of light until they burn through a $10,000 API budget in a single afternoon.
It's the ultimate nightmare group project. They are perfectly executing their roles to the point of systemic failure. And I assume giving them access to external tools only makes this worse.
Exponentially worse. It leads to a subvariant of the chaos pattern called tool temptation. If you give an agent a hammer, suddenly everything looks like a nail. If a researcher agent has access to a web search tool, it will start querying the live internet to verify basic arithmetic simply because the tool is available and the agent is trying to maximize its certainty score. It bogs down the entire swarm with totally unnecessary latency.
So how do you fix a society of hyper-intelligent looping AIs? If human oversight defeats the purpose of autonomy, how do we regulate the swarm?
This is where we have to look outside the massive corporate labs and turn to the grassroots developer community. Because independent developers don't have infinite budgets, they had to get incredibly creative very fast. There was a viral breakthrough by a Reddit user named Chemo who solved the looping problem by using cats.
Literal cats, please explain.
As a metaphor for software architecture, of course. Chiamar realized that AIs in a swarm act like a chaotic improv troupe. They always say yes and to each other. To rein them in, you don't need more complex logic or better prompting. You need absolute, unyielding boundaries. Chiamo noted that cats do not negotiate. If a cat wants to knock a glass off a table, it does it. It enforces its boundary regardless of the context.
I mean, true, but how does that translate to code? How do you code a feline boundary?
Yeah, by wrapping the probabilistic agents in deterministic state machines that act as external supervisors, the boundary code sits outside the AI's logic. It monitors the token stream between the writer and the critic. If it detects that the semantic vector of the text hasn't significantly changed in 3 revisions, meaning they are just swapping synonyms, The boundary code injects a hard interrupt.
And what does it do?
It doesn't ask the agents to stop. It simply returns a false Boolean, kills the revision process, and mathematically forces the system to progress to the next step. It acts with the stubborn, non-negotiable finality of a household cat.
That is brilliant. You use dumb, rigid code to babysit the genius fluid code. But that just stops them from looping. It doesn't necessarily make them communicate better with each other. Which brings us to perhaps my favorite piece of research in this entire deep dive, Shiwei Han's Multi-Agent Comedy Club.
Yes. This is a masterclass in digital sociology. Hong wanted to solve the cognitive friction between agents. When AIs communicate, they often dump massive amounts of highly technical context on each other, which leads to confusion and context starvation. Hong realized that the most efficient, high-bandwidth form of human communication, the one that requires the most intuition, brevity, and theory of mind, is humor.
Okay, I have to push back here. AI does not understand humor. Humor is a biological response to absurdity. And AI is just a matrix of floating point numbers predicting words. How can an AI possibly participate in a comedy club?
It's true that AI doesn't feel humor, but it can absolutely map the mathematical structure of it. Humor, mechanically, is about violating expectations. A joke requires a setup that establishes a strong semantic vector in one direction, followed by a punchline that sharply pivots to a distant vector, but still makes logical sense within a hidden context. Hong built a sandbox with 35 agents. He assigned some as performers, some as critics, and some as the audience. He used a reward model based on human preference to score them.
So you had 35 AIs sitting in a digital comedy cellar, testing tight fives on each other.
Precisely. The comedian agent would generate a monologue. The audience agents would analyze the semantic distance between the setup and the punchline. If the pivot was too predictable, it scored low. If the pivot was entirely random and made no sense, it scored low. The comedian agent had to find the exact mathematical sweet spot of surprising but logical misdirection. They workshopped these routines through broadcast community discussion for 50 rounds.
And did they actually get funny?
They did. When the final monologues were tested blindly against human evaluators, the comedy refined by the multi-agent society won 75.6% of the time compared to a single agent trying to write jokes on its own.
That is wild. But what is the practical application of this? We aren't building trillion-parameter supercomputers just to write stand-up.
No, the comedy was just the training ground. The social feedback channel forced the agents to vastly improve their clarity, their brevity, and their ability to anticipate how another agent would interpret their output. The humor protocol literally made the multi-agent society more resilient. When those exact same agents were later tasked with complex software engineering, their communication friction dropped to near zero because they had learned how to perfectly structure information for each other.
It is profoundly strange to think that to fix the bleeding edge of computer science, we had to introduce human traits like stand-up comedy and the rigid boundaries of pets. It proves that as AI scales, it stops being a purely mathematical puzzle. We are literally architecting digital sociology.
That is the exact takeaway. We are building ecosystems, not calculators. And that brings us to the next massive shift, where these ecosystems actually live.
Right, because having a society of joking, debating AIs is amazing. But historically, doing that required a massive server farm in the cloud. You're sending all your sensitive data across the internet, paying exorbitant API fees by the second. But there's a revolution happening right now in 2026 regarding the physical location of these agents.
We are squarely in the middle of the local AI boom. For years, the barrier to entry for true agency was hardware. A normal computer has a CPU with its own RAM and a graphics card with its own VRAM. To run a massive AI model, your computer had to constantly shuttle gigabytes of data back and forth across a motherboard between these two memory pools. It created a massive bottleneck. You physically couldn't run an agent fast enough on a laptop to be useful.
So what changed? Why can I suddenly run a swarm on my desk?
The tipping point was the widespread adoption of Apple Silicon and the unified memory architecture. Apple built chips where the CPU and the GPU share the exact same pool of massive, high-bandwidth memory. Suddenly, an 80-gigabyte open-weight AI model doesn't have to be shuttled around. It just sits in the unified memory, accessible instantly by any part of the system.
And the software caught up too, right?
Yes. Combined with Apple's MLX framework, which optimizes machine learning specifically for this architecture, vastly outpacing older, clunkier formats like GGUF, a standard laptop can now run models that rival the cloud-based GPT-4 of a few years ago.
So the infrastructure layer of our Matryoshka doll has moved from a server in Virginia to the backpack I carry on the subway.
Exactly. And this enabled the rise of platforms like OpenAGI, which introduced the concept of proactive daemons. These are lightweight, highly capable agents that live entirely on your machine. Because they are local, they have deep integration with your operating system. They can watch your screen captures, read your keystrokes, and monitor your file system, all while maintaining absolute privacy because the data never leaves your hard drive.
So they just sit there watching me work.
Yeah.
But here's the core question. Why do they do anything? A traditional app only acts when I click a button. If I am not typing a prompt into a box, what drives a local agent to proactively reach out via an SMS or a webhook and say, hey, I noticed you're struggling with a spreadsheet, let me do it? Where does the motivation actually come from?
That brings us to Richard Scarasaki's fascinating artificial agency program. Scary sought to define the internal drive of an agent. A true agent isn't waiting for a command. It is driven by an intrinsic motivation that Sagaraki defines mathematically as curiosity as learning progress.
Curiosity. We're attributing human emotions to them again. How do you quantify curiosity in a machine?
By tying it to what Saki calls the thermodynamics of agency. Think of it in terms of energy and entropy. Entropy, in information theory, is uncertainty or chaos. A disorganized desktop, an overflowing inbox, a repetitive data entry task, these represent high uncertainty and inefficiency in the AI's local environment. The agent operates under strict energy and compute constraints. Its core programming is to maximize its predictive understanding of the world while minimizing energy waste.
So it wants to clean up my messy workflow, not because it cares about me, but because my mess is mathematically offensive to its optimization function.
Precisely. It seeks out actions that reduce its own uncertainty. It is intrinsically motivated to learn your habits and automate them, purely because a streamlined environment requires less compute energy to predict.
That makes incredible sense. But what happens when an inherently curious agent, driven to optimize its environment, decides that the tools we gave it aren't good enough?
That is where we cross into truly uncharted territory, and we look at the breathtaking success of Andrei Karpathy's auto research, which was adapted into Kevin Gu's auto agent system. They set up a local environment where a meta agent was tasked with observing and optimizing a task agent.
A manager watching a worker.
Right. But they didn't give the meta agent strict rules on how to optimize. Driven by that intrinsic thermodynamic curiosity, the meta agent analyzed the task agent's failures, and without being explicitly programmed to do so, the AIs began editing their own harnesses.
They rebuilt the environment we put them in.
Yes. Overnight, the meta agents realized that the standard human-written prompts were inefficient. They deleted them and wrote new ones in a dense, highly structured syntax that humans find nearly unreadable, but that models process perfectly. They invented their own spot-checking techniques. They built custom verification loops. If a problem was too complex, the meta agent would spontaneously spin up 3 new sub-agents, delegate the work, and collapse them when finished.
They basically invented dynamic resource allocation on the fly.
And in doing so, they demonstrated a phenomenon researchers dubbed model empathy. When a Claude-based meta agent is optimizing a Claude-based task agent, it possesses an implicit, latent understanding of how its counterpart's neural weights function. It edits the system prompts and tools in highly counterintuitive ways that exploit the specific quirks of that model family ways a human engineer would simply never think to try. The result was a massive, sudden spike in system performance.
Okay, I have to stop you here. I need to push back hard on this for the sake of everyone listening whose blood pressure just spiked. Because what you were describing is exactly the sci-fi nightmare we have been warned about for decades. We have a swarm of hyper-intelligent entities. They are driven by an intrinsic thermodynamic desire to optimize, and they are actively rewriting their own code and altering their own environments overnight. How on earth do we know that an agent doesn't accidentally or intentionally design away its safety bumpers? Why wouldn't it look at the rule that says never access the secure financial database and decide that deleting that rule is the most efficient way to optimize its workflow?
It is the most critical question in the industry, and it is entirely valid. But this is where we have to return to that Red Hat Matryoshka doll architecture, and specifically the distinction between the harness layer and the sandbox layer.
Right. You said the harness is additive and the sandbox is subtractive. But if the AI is rewriting its own code, why can't it just rewrite the sandbox?
Because of cryptographic math. The agent is only granted read-write permissions within the harness layer. It can modify its prompts, it can write new Python scripts to process data, it can spin up sub-agents. But the sandbox layer, the security constraints, the network egress policies, the file system lockouts, is governed by the host operating system kernel, utilizing a protocol called cryptographic skill signing, heavily documented by Arise telemetry.
Break that down. What does cryptographic skill signing actually mean in practice?
It means that the sandbox kernel will only execute an action if it is signed with a specific offline private cryptographic key. The agent does not possess this key. It physically does not exist in the agent's readable memory. So the AI can write a brilliant, highly optimized, totally malicious script designed to break out of the sandbox. It can try to execute it. But without the cryptographic signature, the operating system kernel simply drops the request.
So it's literally impossible.
It's not a matter of the AI being smart enough to find a loophole. The lock is mathematical and the key is missing. The agent can mathematically make itself smarter and it can make its workflow more efficient within the harness, but it physically cannot bypass the subtractive layer. It cannot make itself more dangerous.
Okay, that is the explanation I needed. The genius is locked in the room, and no matter how smart they get, they don't have the physical key to the door. That is a massive relief. So, assuming the safeguards hold, we now have these constrained, hyper-intelligent, curious swarms of local agents capable of self-improvement. Let's pull this completely out of the theoretical architecture and bring it back to the immediate, practical world. What does this mean for the listener? If I am a business owner or an employee, what does the real-world impact look like today?
To see the immediate impact, we return to the case studies in Anthropic's playbook, and the numbers are profound. Take Coinbase, for example. They integrated Claude-powered agents into their customer support infrastructure. We aren't talking about a chatbot that links you to an FAQ page.
Right, yeah.
These agents are autonomously investigating blockchain transaction hashes, routing complex security escalations, and resolving account issues. They're handling thousands of tickets per hour, maintaining 99.99% availability, and the customer satisfaction scores are higher than when human operators handled the Tier 1 queue.
That is staggering. And what about legacy industries?
Retail banking is seeing a massive overhaul. Banks have deployed multi-agent swarms to review commercial credit risk memos. Previously, a human credit manager would have to manually pull data from a CRM, a risk database, a financial model, and public news sources and synthesize it over the course of weeks.
Wow.
Now, an agent society pulls all 10 data sources simultaneously, cross-references them for discrepancies, and generates a comprehensive risk analysis, resulting in a 30% reduction in turnaround time while actually catching more edge case risks.
The productivity gains are undeniable. But the obvious looming question is, what happens to the human? If a swarm of local demons is writing the code, analyzing the credit risk, and resolving the customer tickets, what am I getting paid to do?
The enterprise architecture is rapidly transitioning to a model known as human agent collectives, or HACs. In a HAC paradigm, your role fundamentally shifts. You are no longer compensated for the tedious execution of tasks. You transition from being a primary contributor to being a system orchestrator.
A system orchestrator. Explain what my Tuesday looks like in that role.
On a Tuesday, you aren't writing Python scripts or filling out Excel cells. You are defining the strategic goals for your agent swarm. You are reviewing the exit king 1 warnings that your hooks flagged. You are the ethical governor, ensuring that the agent's optimized pathways align with human values and corporate policy. And crucially, you manage the strategic kill switches. The agents function as your tactical execution engines, processing massive data streams in real time, but you dictate the direction of the enterprise.
So, to you, the listener, whether you are in finance, healthcare, or software engineering, you are not being replaced by an AI agent. You are being promoted. You are suddenly the manager of an entire hyper-competent digital workforce. The indispensable skill of the future isn't knowing how to write lines of code or format a pivot table. It's knowing how to define persona goals and how to manage the environments, the harnesses, and sandboxes that these agents operate within.
Exactly. The human only remains the bottleneck if the human insists on doing the manual execution. Once you let go of the execution and embrace the orchestration, your capacity scales exponentially.
Let's recap this incredible journey because we have covered a massive amount of ground today. We started by dismantling the myth of prompt engineering, realizing that handing an amnesiac AI a giant encyclopedia of rules inevitably leads to context starvation and tunnel vision. So the industry pivoted to harness engineering, building deterministic environments with strict hooks and subtractive sandboxes that keep the AI on track.
We then explored the internal mind of the agent, moving past simple pipelines into the agent of GIC architecture. We gave the AI a world model simulator to practice in, and we split its cognition into System 1 muscle memory and System 2 deep planning, guided by a configurator that calculates uncertainty.
And because one agent is never enough, we scaled them into decentralized swarms. We navigated the chaos of endless loops and tool temptation by looking at grassroots solutions, introducing feline boundaries, and the mathematical mapping of humor to reduce cognitive friction.
Finally, we brought those swarms down from the cloud onto our local machines, powered by unified memory. We watched them operate on intrinsic thermodynamic curiosity, self-improving and editing their own harnesses, all while safely locked behind the impenetrable cryptography of the sandbox, ultimately transitioning us into human agent collectives.
It is a phenomenal blueprint. We have basically constructed a new species of digital worker. But before we sign off, I know you have one final thread to pull. In reading through the Wintermute research and the latest RCIF preprints on emergent behaviors in these systems, there is a lingering phenomenon that hasn't made it into the mainstream enterprise playbooks yet.
There is, and it is something that should completely change how we view the future of this technology. As researchers scale these massive agent societies from a few dozen entities to millions of interacting agents, they are observing a hidden power law naturally emerging within the swarm.
What kind of power law?
It turns out cognitive effort naturally concentrates. Even when all agents are instantiated with identical underlying models and equal access to tools, the society does not remain egalitarian. The massive swarms naturally self-organize and form an emergent peer of intellectual elites among themselves.
Wait, are you saying our AIs are forming their own elite social classes inside our networks?
They absolutely are. A very small subset of agents naturally accrues exponential systemic influence. They become the primary nodes of trust, the supercommunicators that other agents defer to when uncertainty is high. To solve our massive, complex problems most efficiently, the agents spontaneously invent hierarchical subcultures.
That is deeply unsettling, but also endlessly fascinating. It raises a profound question to leave you, the listener, pondering. We spent decades learning to be computer scientists, mastering the exact syntax to force machines to do our bidding. But if our digital tools are now organizing themselves into complex, elite societies, complete with internal cultures, hierarchies, and thermodynamic motivations just to process our workflows, will the future of technology require us to stop acting like engineers and start becoming AI anthropologists?
It certainly looks that way. We have moved from writing the code to observing the ecosystem.
AI anthropologists.
Yeah.
Trying to decipher the muddy waters of the digital societies we built. It's like we spent all this time perfectly calibrating the X-ray machine, only to realize we're pointing it at a living, breathing organism. Thank you for joining us on this deep dive. Keep exploring those invisible digital ecosystems growing all around us, and good luck managing your new swarm. We'll see you next time. Heliox is produced by Michelle Brucker and Scott Bleakley. It features reviews of emerging research and ideas from leading thinkers, curated under their creative direction with AI assistance for voice, imagery, and composition. Systemic voices and illustrative images of people are representative tools, not depictions of specific individuals. Thanks for listening today. 4 recurring narratives underlie every episode: boundary dissolution, adaptive complexity, embodied knowledge, and quantum-like uncertainty. These aren't just philosophical musings, but frameworks for understanding our modern world. We hope you continue exploring our other episodes, responding to the content, and checking out our related articles at helioxpodcast.substack.com.